So is it visible to you?
Yes,
Yes, sir.
sir.
Okay, so we are here last day that we understood that filtering problem is basically multiplication in frequency domain. Okay, and then we want to know what is the corresponding operation in time domain. So we'll actually provide these operations in a way that it is convolution. So the operation in time domain would be of this kind. Now, how can I prove that if we do this operation, then we'll get multiplication operation in frequency domain? So we can start with actually this expression, and so we can start with doing the Fourier transform of this. So everybody is familiar with the Fourier transform. Are you familiar with Fourier transform?
No, sir. Like in network theory class, it was just overview was given, not detailed. It was not taught.
Okay, okay. So let us start with this. Now I have a signal, say xt, okay, and I want to get the Fourier transform, which I can denote as x omega. Okay. Now you should not get confused with the notation. In this case, I will be doing continuous transform, but the same thing can be executed in case of digital domain also. Only difference will be that integration will be replaced by summation. Okay. Now the expression is like this, that we can find this x omega as minus infinity to infinity x of t, the function, into e to the power minus j omega t dt. Okay. Now this e to the power j omega t or minus j omega t, we call it as a kernel. And if you observe minutely, then I can think that this e to the power minus j omega t as one function, and then xt as another function. And if you minutely observe this integration, this is nothing but the inner product between these two. Now, what is inner product? It is analogous to dot product in vector space. Now, what is dot product? If I have, say, some vector r equal to xi plus yj or x1, y1 plus z1 k, and another vector r2, say, I have x2i plus y2j plus z2k, and then if I go for dot product between R1 and R2, what we do? We do the corresponding term multiplication and sum it, right? So x1, x2 plus y1, y2 plus z1, z2. Now you can see we are multiplying the corresponding term and then summing it up. Similarly, that sum is replaced by integration, and this is one signal xt, any signal, and so this is our xt, and then we may have another signal e to the power minus j omega t with certain uh, frequency omega. Now you can see that at particular t, this xt value, which is this one, and then multiplied by the corresponding value from the e to the power minus j omega t. Okay. So this can be reversed. I am just trying to convey the concept. So this e to the power minus j omega t might be like this or so, or let us see, at infinity it will be 1. Yes, sorry, minus infinity, so 1 by infinity, so 0. Okay, so this one. So what is our means what we need to observe here, that whenever we are going to get a transform, we are doing what we are doing. We are taking the functional value at certain moment and then multiplying at the same moment a kernel. Now, when this is e to the power minus j omega t, we call it as a Fourier transform. When it is e to the power minus st, we call it as a Laplace transform. So like that, if we change the kernels, we can get different transforms. Okay. Now, what we want, now we have another function, what we call as impulse response of a system, and that is actually giving us the characteristics of a system. Now, why it is giving us characteristics of a system, I will discuss. But before that, let us prove that the multiplication in time, frequency domain is actually the convolution in time domain. So we have this f, so we can denote it as h omega, and in similar way, this h omega would be what? H of t e to the power minus j omega t dt. Okay. Now we'll take the expressions of output of the system yt, which is in this form, x of t and then h of t minus, say, some value tau, and then e to the power minus j omega. Now you can see the integrating term variable will be tau. Okay, d tau. Okay. Now what we can do, we can go for y of omega. And what is that? So we can do y of t e to the power minus j omega t dt. This is the Fourier transform formulation, what we just said it for x omega and h omega. Now what we can do, we can get this yt expressions into it. So we have xt, then we have h t minus tau, then we have e to the power minus j omega tau d tau, and then we have minus j omega t dt. And now what we can do, I can just cluster these tau components, okay, into one segment. And so I will be doing e to the power, so this is xt, and then integration over this h of, sorry, t minus tau e to the power minus j omega tau d tau, sorry, d tau, and then e to the power minus j omega t dt. Now you can see that this part, or what we can do also, okay, so let us erase this part. And let us see from this, then what is this one? Okay, now if I place, say, h of t minus tau, then e to the power minus j omega tau d tau, integration minus infinity to infinity. Now if I take t minus tau as some variable, say p, okay, then tau would be t minus p, okay, and therefore if I replace it, and you can see from here that this d tau would be equal to dp minus, so we can easily interchange these minus sign also here with the, means if you see from here that when tau varies minus infinity, p varies plus infinity, and then when it is plus infinity, okay, so p varies minus infinity, and then minus sign can be taken in this, and so what we can get, h of p, then e to the power minus j omega t minus p dp. So now this minus e to the power minus mm, yeah, yes, so we can take this e to the power minus j omega t. I think I have made a mistake.
Sir, that yt will be x of tau h of t minus tau. There will be e to the power minus j omega tau will not be there. In convolution formula is you have in the last slide you have written there. So
Yes, yes, okay, let us see. uh no, no, this okay, okay, yes, yes, okay, so this one would not be there. Very good. Yes. So we can remove of this. Okay. Very good. So now the things will be a little bit easier for us now. So if I take e to the power minus j omega tau
yeah.
in here,
Excuse me,
then
sir.
I can take, yes, tell.
So that will be x of tau, I think.
Which one?
Sir, y of t is equal to minus
Ah,
infinity to infinity x of tau. You have written x of t.
yes, yes. Very good. Yes, this should be x of tau. Very good. X of tau. Okay. So what we can do now, we will be taking this as tau, and now this tau d tau, so sorry. So we'll be changing this one. So we'll be just rearranging that part, huh? Okay. So what we'll be taking here, we'll be taking this t minus tau, okay? And then what will come here? This is plus tau, so minus j omega tau d tau, and here we'll get the dt, right? Now you can see that if we take this t minus tau as one variable, then we'll get, so here now our task is Okay, so now we'll be in comfortable, sorry, zone, that our task is t minus tau, and then we have dt, right? Now if I say t minus tau equal to this, then we have this dt equal to dp, and so our expression should be that minus infinity to infinity h of p, then e to the power minus j omega p and dp, which is nothing but h of omega, right? Okay, now get this one. Now if that is the case, then what will happen? We can actually segregate this, because now this is a function of omega. So we can segregate that h of omega expressions out of this integration, and then we get x of tau and e to the power minus j omega tau d tau. Okay, and so which is again, this expression is nothing but x omega, and so we get this is, okay, is that clear to you? I hope so. Hmm? So what we find, that this convolution operation in time domain can be, so now you can see, observe that I have used in my expressions x tau ht minus tau. In this I have used h tau xt minus tau. Both will come to same conclusions, that it is the multiplications in frequency domain. Okay, so we understood that. Okay, so now this is convolution, and now we want to do it in digital system, digital processor. In this case, what we have shown, it is the time is varying from minus infinity to plus infinity, which is not possible when we go into our system. And so we cannot take infinite number of terms. We cannot take, so for that reason, what we need to do, we need to express it in digital form. And we can prove the same, that whenever we go to sampling of the signal, what happens, that the signal becomes periodic in nature. That means whatever value of these component are within certain zone, it is repeating again across the sampling frequency. So that part I am not discussing here. You can get it from a book on digital signal processing called by Prokis and Manolakis. Okay, so the band can be of like this, and therefore we can only work on these which corresponds to this expression, this 0 to m minus 1, and we call it as a DFT, discrete Fourier transform. Okay, now discrete Fourier transform, this expressions comes due to the sampling. As I said last day, what is sampling? So when we sample a signal, so I may have some signal xt, and when I get these samples, say on these paths, and then we do the Fourier transform of it, discrete Fourier transform, so then we can see that this becomes that one. So if the band of this signal is this one, this is replicated in the, or becomes periodic in the frequency domain. Okay, and since this is periodic in frequency domain, we can only work with the one period, and so that period becomes to be ranged between m equal to 0 to m minus 1. Okay, and there, so thus we can derive this expression. Now what happens here, that we now get finite number of computations, so this hn and xn minus 1 can be computed. But observe this, what is this one? Now if, say for example, n equal to 0, so what we'll get, this m minus 1, h of 0 and x of minus m. So what are those values? Those values are nothing but the past values of x. So it means that we need to store some past values of x. Then how many past values of x is needed? We can prove that this m number of past values are needed to compute this n yn. Okay. Now, if that is the case, what will happen to our output instances? That means I am placing one signal at certain point or certain value, say this one, and this is my, say, xn, but I need all the past values of xn, and once the xn will come, then only we can come after yn. Okay, so it means that the moment this xn is given, so if I plot it in same time instance and my xn is here, so this is my xn, I will not get the yn at same instance. It will take some time, and I will get the yn, say this value, which is my yn for xn. Okay, so I will have a time delay between these two instances, and we'll be calling that time gap as latency. That means the output corresponding to the input xn will be having a delay from that instance of the input. Okay. Now this will not affect our speed, because I can take the next sample and I can get the y at this. So what will happen in effect, that initially for some number of samples will not get proper y, but after that only we can get some y. And so this is nothing but the initial delay. And that will be the, again, the latency. And it happens for any system, the moment you are switching on the system, it will not produce the output immediately. It will take some time and give a stable output after that time. Okay. Now this delay depends on this, how many past values of xn you need to store. Now how can you store that? For that we have memory locations. And in those memory locations, we can store these extents. So might be the x. So we can store the signal into memories, and thus we can get all these x minus n minus m component, x n minus m component, and then we can have another memory location where we can put our hn. The, because this has 0 to m minus 1 number of coefficients, this Hn. So we'll again have number of samples. And we can do this instantaneous multiplication and sum using the instructions of the processor. Is it clear to you? Tell me. Hello?
Yes, sir.
Anyone having any question on this? Please raise this question instantaneously so that we can clear our doubt. Because I am trying to make it brief, although you will be studying this in your DSP course. So I am coming back to this figure again, that digital implementations of the filter. So we have shown you that before we go for the filter, we need to sample. Now once this sampling is done, our job becomes easier because the signal becomes periodic in nature, and then we can work only on the one period, and that's why we come up with a finite number of computations. And see now how to execute that finite number of computations, where we observe from the expression that we need to store number of past values of the signal. Okay, past values means with respect to the current instance, the n. So xn minus 1, xn minus 2 up to xn minus m plus 1. If the filter order, we'll call this m, capital M, as the filter order. Okay. Now depending upon filter order, our latency will change. So as I increase the filter order, our latency will be increasing. If I decrease the filter order, our latency will be decreasing. But decreasing the filter order will affect the frequency response of this. That means this Yn. Now what is our objective in case of filtering? Our objective is to nullify this noise component. So noise region. Okay. So we want to put it to 0. But if we reduce the filter order, so what may happen, that we can see that this is up to this omega c is maybe there, but after that, beyond that, this signal may not be exactly 0, but we can have some oscillations or so. And therefore you can see that we can get some non-zero component in the noise zone also. For what? If we reduce the filter order, which is equal to m. So the frequency response will change. Now what is frequency response? Nothing but the Fourier transform of the ht. So the impulse response. So Fourier transform of impulse response, we will be calling it as a frequency response. That means if I give different frequency sinusoids to the system, I will get certain expressions of that, like this. So which is our y omega, and we are at a time we are giving say sine of say 50 hertz, then sine of 100 hertz, then sine of 150 hertz, and we are measuring what is the value here. Okay, and then we are getting a curve which we'll be calling as frequency response curve, and which is again nothing but related to this impulse response. So this h omega will be that frequency response, will give us that frequency response. Now one question I remained, that what is this, why we are, you know, interested or to find the impulse response of a system. Okay, now even if you are at the preliminary stage of this Fourier transform in your network theory course, I think you were doing this finding Fourier transform of different functions, and particularly this impulse function. Then you have also done something on step function, isn't it? As I said last day, that our class should be interactive. Okay, so even if you may have some questions which you may feel that others will think as silly, you can raise your question. No problem, even if it is a silly question. Okay, but always try to clear your doubt. So, what is the impulse response? As one of you said last day, that if I give delta t to a system, then whatever output we get, that is nothing but the impulse response of the system, and that is basically a model of that system. Okay, so that we'll call it as a impulse response. Now our question is why this can be taken as a model of the system. So now what we'll be doing, we'll be trying to find this Fourier transform of this delta t, and we'll be trying to have a picture of that in the frequency domain or the Fourier domain. Okay, so I want this answer from you. What is the Fourier transform of an impulse function?
Sir, 1.
1. But what does it mean in this graph?
If,
How it will look like?
the amplitude of every frequency component is relatively same.
Yes, so that means how this graph will look like in frequency domain?
Constant
Straight
function.
line.
Constant one.
Straight line? No,
Yes.
you cannot, you should say very clearly, straight line parallel to the omega
Yes.
axis, right? This frequency axis. And this means that I have 0, that means DC component. I have omega, then I have twice omega and thrice omega and so on. So for all these frequencies, this is constant. Not only that, but also all these harmonically related frequencies are present in this impulse function. And what does this mean? This means that if I apply the delta t to a function, that means I'm exciting the system with all these frequency components. That means whatever output I am getting, which is corresponding to all these frequency components, which are harmonically related, right? And now I want to apply any signal xt. Now any signal may not have these characteristics, but maybe only say this part, that means the band of that signal for this xt. So this is applied to this. Now I know the response for all the frequency terms, right? And out of that, a partial band of frequency constitute this signal, any signal which we can apply to it to this system. So definitely if I know the whole, I can know definitely for the partial one, right? And that we can get it from this xt, and we'll denote this as convolution of h of t. So what we understand from this discussion is that the impulse, applying impulse to a system means that exciting that system with all the harmonically related frequencies, infinite number of such things. And since we know the response of that system for all the frequencies, then we can definitely know the partial number of frequency components response towards means when it is subjected. And then any partial combinations of these frequencies will give us the signal which is available naturally in our day-to-day life. Okay. And therefore, if I know the HT, the impulse response, we can characterize the system or we can model that system easily. Right? Okay. Now we have a certain point that how to get this HT, and so the question how to get the HT. Okay. This essentially is equivalent to what we'll be calling as filter design. Okay. So this will be nothing but that filter coefficients. So how to get that filter coefficients? Now what will be our input? So input to that will be the frequency response, this h omega, because that is easier for us to understand that we should have some cutoff frequency, we should have this pass band, we should have this stop band. So those we can easily specify, and from there we need to find this HT, which we'll be calling as filter design. So whenever you will be studying this DSP, you should also focus on this filter design, how to design that filter. Okay. So for the time being, we can assume that filtered coefficients are available to us, and with that we can easily compute, as I said, with the convolutions, this with this finite amount of computations, we can easily compute this yn, which is the filtered version of the noisy signal, right? So what we need to understand that when we are going to, so this digital processor paradigm, then this is only a platform of implementation. Okay. Now what to implement? So that knowledge also should be there with you. And for that, we are particularly interested in signals because we found that there are a lot of signal processing tasks involved in our day-to-day life, in engineering or in any technological systems. Okay. And so we have the signal processing or any engineering area. Now, how to implement that signal processing? We need a mathematical model. We have found that mathematical model of one such signal processing, which we are calling as signal filtering. Okay. And that filtering is nothing but a convolution process. Now, the convolution can be executed with a set of computations, which is nothing but the multiplications and additions. And so we could develop a arithmetic operations which can be utilized for computing this filter operation. And now everywhere what we can find that so this is one operation, okay, filter operations. The another very often we have seen just now that we may do our computations in the frequency domain also, and then our operations is simple multiplications in the frequency domain. Now that is we'll be calling as a signal transform. Signal transform is what? Is nothing but the mapping or function. Now you can see that the signal here, in mathematical domain we call as a function, but in signal processing we call the same thing as this signal. So signal is nothing but a functional representation. So it maps one vector to another vector. Okay. So like for example, that voltage can be thought of as sine omega t plus phi that we have seen earlier, right? So this is a function, and we can also think the same function as an operator, because you can see that this ht or hn is nothing but a function also. We are getting number of samples, and so we can have number of means we can represent the function as an operator also. So don't get confused that this function in one set, so while this ht is the operator and xt is the signal, but both can be represented as a function. So what is this transform? Just like say we have this x as a vector in this space, and if we multiply a matrix with that, we'll get another vector in another space. Okay, we can also have some kernel, so which actually transform all the vectors into zero, this origin of that. Okay, so essentially for a linear system we can represent that as x equal to y or x equal to 0, and solving those two and combining the solution, we can get the final solution as y. All these things we can do through this digital processor. So xt we are giving, we are multiplying with a. Now a is a matrix, so the operator, so we can have a corresponding dft operator. So this can be a dft operator which we have just discussed, and then we can get the y. So now we'll be little bit trying to understand that what is transform. Okay, and for that we'll take help of our past knowledge. Okay, anyone, if anyone having unmuted, you mute yourself. Okay, so let us see an object in motion. We have already studied this in physics, that we give a force which is our input signal ft, we have an inertial system, and then we get a change in position pt, which is the change xyz, which is our output signal. Now if I want to means derive this position, then what we do in physics, can anyone tell me? Hello.
Yes, sir.
Huh.
Yes, sir.
Tell me how we can get this pt from given ft. What is the procedure we have learned? This is from 12th standard physics.
We can have a frame of reference.
How to derive that? What we do with this Ft? Ft is given to us. And I want to know the effect of Ft on the inertial system, the resultant effect. Tell. Tell even if you are incorrect. But that will recapitulate our earlier knowledge. It will help us to recollect, huh? What? Or you have forgotten?
Sir, Ft is the force over here, right?
Yes.
So then by integrating force, we can get the momentum.
No, means don't think Pt as a momentum. Think it as a effect, means position changes. Okay. So what is the basic of means approach? I am focusing on the approach. What should be our approach to find this Pt?
So we should resolve the F into three components, x along
Very
x
good,
along y
very
and
good.
z.
But you have to refine your statement that we need to resolve or project this Ft into three orthogonal components, right? That means this vector must have dot product 0, right?
Yes, sir.
And then, but why we do that? Because of this orthogonality, any changes in any dimension will not affect the changes in the other dimension, isn't it? So that means we can separately work on each of these dimension and then finally add all these effects. So what we do, we resolve these Ft into three dimensions which are orthogonal to each other, and then we get these corresponding position changes in the each dimension, and then we finally add all these and to get this Pt. Is it correct? I think now you can recollect that, everyone.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes.
Sir, can you mute Mohammed Sadiq, like his mic is unmuted?
Okay.
Yes, sir.
And he is not attending. Okay. This is visible to you?
Yes, sir.
Okay. So what we did, we get a Ft, we resolve it into three orthogonal dimensions, then we take the effect in each dimension and then we add it up. Okay, so that is the concept we learned in our vector operations in physics. Now, what we want, now we are replacing that, you can see this Ft by a signal. Okay, and so this is xt, and the inertial frame by a matrix A, which is a model of a system. That can be that inertial system also. And then yt, the positions of the output as yt. So now our signal is xt, input signal, system is A and output is yt. Now our question is, can we do the similar approach? Can we take the similar approach in case of function also? And for that, what we need to know that whether we can represent a function as a vector or not. Okay, and we can do that. We can do with very simple idea that say I have infinitely spreaded function, and because of our need of or demand of finiteness, we can take a window over that, and starting this part as the current sample, digital samples, and all our past samples, we can arrange those samples in an ordered set, right? And so this can be considered as a vector. So ordered set of numbers, we call it as a vector. And therefore, we can represent this xn as a vector in these orthogonal systems. Okay. Not only that, if we convert this with the transforms, then we can get the corresponding transform value xk, x, k1, k2, and so on, km. Okay, and that is also a vector. So we can represent the signal in the original domain with a finite set of samples as a vector. We can, if we convert that same vector into say Fourier domain or so, that can also be represented by a vector form. And so the signal can be thought of or represented as a vector, ordered set of numbers or samples. And so what we can do, we can think or represent that xt in terms of x omega 1, x omega 2, and x omega 3. Now you can see or you can remember the expressions of Fourier series. And what was that? Minus infinity to infinity, an cos n omega t plus bn sine n omega t. We can represent any signal, and particularly here I am talking about periodic signal, which will have the Fourier series expression. The same logic can be transferred or extended to aperiodic signal also. And in that case, this Fourier series expression will be replaced by Fourier transform. Now you can see the analogy between our force system or inertial system and the signal. So now you can see that what is ft? Ft is nothing but sum of this fxt plus fyt plus fzt. Now, if we take this as a value, then we should place I, j, and k. Now you can see that we have these values, the coefficient values into I, coefficient values into j, coefficient values into k, and we sum it over that. Okay, so what does it mean? I can say that ft can be considered or expressed as a linear combination of I, j, k, right? If I come to this expression, we will see that this xt is a linear combinations of sinusoids. and therefore this cos n omega t, sin n omega t, these are analogous to I, j and k. Now what are I, j, k?
Component in XYZ direction.
No, we have a term for that. In physics we call it, what we call it? It's very simple. I am not asking any difficult question.
Unit vectors.
Unit vector.
Yes, very good. Unit vectors. And they are orthogonal to each other. What does it mean? If I do I dot j, we'll get 0, right? Now I said these sinusoids are analogous to this. That means this cos n omega t, sin n omega t, n can vary from minus infinity to plus infinity, integers. Okay, so they are also analogous to unit vectors. What does this means? We'll call it as a basis function. Right? And as this is true for this dot product is 0, so we must have some operations for function. Okay, so cos n1 omega t, cos n2 omega t, and we'll denote it as this. And now can you remember what is this operation? Just few slides back I have said this. You must be very careful in listening. Listening is also an important aspect of human subjects. Inner product. Okay. So that means this dot product in case of vectors is analogous to inner product in case of functions. And what is that? The way we do instantaneous means this dimension wise multiplication. Here the dimension represented by this t, so instantaneously multiplication. So that means inner product is nothing but integration cos n1 omega t cos n2 omega t dt will be 0 for any integer value of n and n1 and n2. So what does it mean? If you multiply say cos 50 omega, this is say 100 pi t, which corresponds to 50, and you do the inner product with cos 200 pi t. So if you write this way, integration cos 100 pi t and then cos 200 pi t dt, you will get always 0. You can prove it by your 12th standard knowledge of integrations and the trigonometry. Okay, so I am not going into that. So for any n1, and same thing is for cos sine or sine components. So if the n1 or n2 are different, then the inner product will be 0. That means they form a orthogonal system. So what we are doing, we are resolving this xt into those orthogonal components in frequency domain, multiplying with this say matrix A for each of these dimension. We get the effect in each of the dimensions, and then we again add all these effects to get the final one, which will be nothing but y of t. Okay, add means we are doing the inverse Fourier transform or inverse Fourier representations, series representations. Okay, so what we understood from this discussion, that the signal transforms are also important, and signal transform is nothing but resolving a function into a linear combinations of basis functions, isn't it? And linear combinations of basis functions is easier to understand if we find the analogy between a vector space with unit vectors representations, right? So vector in a vector space can be represented as a linear combinations of unit vectors. In case of function, it can be represented as a linear combination of basis functions. And these basis functions are orthogonal to each other, which is ensured by their inner product equal to 0. Okay. So what we can do, say for example, we have oscilloscope where we can see the time domain variations of the signal. We have also instruments called spectrum analyzer, where we want to know what are the different frequency component available in certain signal, right? So now with this embedded system, where we can go for these DFT operations of the input signal, we get the coefficients, then we can measure the energy of in each coefficients, and you can come across one theorem which we call it as a Percival theorem, which tells that sum of x square n is equal to the sum of ci square. So this is in Fourier domain, and this is in time domain. So this hold because this Fourier transform, so this is true as DFT is orthonormal transform. Now what is orthonormal transform? Okay, orthonormal is nothing but, as I said, that I dot, say I dot I, we get 1, right? Similarly, that cos n omega t, cos say n1 and n2 omega t, and the inner product will be 0 if n1 not equal to n2, but will be 1 if n1 equal to n2. If that condition holds, we call that as a orthonormal transform, that ensures that this transform will not introduce any energy into the signal. So this coefficient directly will be giving us the energy of the signal itself. So what these values are giving us? So this is in the frequency domain, and say this omega, and we have some values in the omega, say this is C1 square, then we can have C2 square. That means this xt contains this particular, say this is omega 1, this is omega 2, and corresponding to omega 3. So these sinusoids, this signal contains this one sinusoid with omega 1, another sinusoid with omega 2, another sinusoid with omega 3, with the amplitude of C1, C2, and C3. And what is the purpose of our instrument is to find those components. So from there, we can conclude directly observing the display. So that means what are needed. Now this whole computations is carried out inside the processor. We have the signal input through this ADC, so we can have So to convert, so we have our signal in analog domain, so we need to convert it into XN, and then these are digital domain, so we can convert it into say Y omega, or we can only directly put these values into the display with suitable form, so graphical display. So we can observe here that we are doing the computations with this processor, within this processor. We are also interfacing the external signals through different peripherals, right? Any questions up to this?
No, sir.
Tell. Try to be interactive. I'm insisting always. If you have any doubt, any one of, if you have doubt, you can raise your question. Okay. Now we'll come to that. We understood that different type of applications where we can apply our digital embedded systems. We understood that this is only an alternative solutions to available other solutions, other set of solutions. And now, while we are talking in the digital domain and particularly the computation, then we need to concern about the issue which is related to the accuracy of the computation, which we are dealing with since our childhood days, the moment we started this addition and subtraction with fractions, with fractional numbers. And very often we were asked to provide the solution or provide the answer with, say, precision up to second decimal position, up to third decimal positions, and so on. Okay, and so the same thing will happen here also, and the terms which we should uh, put our concentration on is this range of the signal or the functional variation. Okay, the precision of the signal or the functional values, and the precision of the domain of or of the signal function. So let us understand with some graph. Now, when we are coming to digital signal, so we need to say what is digital signal. Okay, so we already know that we have these sampling instances. So we are taking our signal at those instances only, and by that we'll be coining one term which is called as quantization of time. Okay, so sampling is nothing but quantization in time. Okay, is it understood how this quantization term is related here? If you can remember the atoms structure and the quantization numbers, where it is told that the electrons orbits cannot take any orbits or any positions in that, rather a fixed set of orbits are present, and that is means defined or represented by quantization numbers, right? So here also we are telling that these samples are only available at these points of time and not in between any places. And therefore we are effectively quantizing the time scale or time dimension. And when we going to present a value in a processor, there also we have a fixed number of wires and a collective set of that numbers, we call it as a bus. Now each bus can have its state either 0 or 1. Okay, each bus. So don't tell that digital signal which can only take 0 and 1. We have to tell that this number of buses will be at particular state. So that means, say for example, if my number of buses are 3, so the length of bus, length or width, rather we will use that word width. So width of bus, say equal to 3. What does this mean? That each can take this 0 and 1. So how many combinations are possible? Anyone?
Sir, 2 power 5 combinations?
No, it's a 3, na? So how it comes 2 to the power 5?
Yes.
8. Sir, 8.
8, 2 to the power 3
Simply
actually.
2 to the power 3,
Ah,
sorry, sir.
yes, yes.
5 times.
So we can have 0, 0, 0, then 0, 0, 1, then 0, 1, 0, 0, 1, 1, like that. Huh? And so how does this affect? Now, this can be, this value, which is all 0, can be represented as 0, 0, 0. This value, the next one, can be represented as 0, 0, 1, which is nothing but 1 LSB difference, we call it. Then 0, 1, 0, and so on. Now, what happens any value in between? We cannot. We cannot show that value, or we cannot represent any value in between. Okay? And now we want to represent say 5 volt. So our xt range between 0 to 5 volt. And we are trying to represent that 0 to 5 volt with the help of 3 wires. Okay? And therefore the 001 will be representing how much voltage? We can get it easily 5 divided by 2 cube, because we are dividing this whole range 0 to 5 by 8 number of states, 8 number of values. Okay, and therefore whatever value we'll get it out of this 5 by 8 volt, say we are measuring this in voltage. So this 1 LSB difference is basically the 5 by 8 volt. Now this 010, then what will be that value 010? So this will be nothing but 10 by 8 volt, and so on, and ultimately it will reach to 5, closer to that. Understood? Now effectively what we are doing, so dividing the range into number of different distinct values, and which we can call it again the quantization. But in this case, quantization in sample values, right? So
Sir,
digital
hello, sir.
tell. Hmm. Tell.
Sir, is it same as hello, sir? Is it same as resolution?
Yes, resolution. Very good. You are correct. Hmm. So
Sir, but
this is
sir, but in hello, sir. Sir, but in resolution, we divide it 2 to the power n minus 1. Actually, we divide the total number of steps. So, like in 8, there, like a 0, like we have 3 bits. So,
hmm,
there will be 8 combination. But the lower level 0, it will be remember 0. But the number of level, like number of steps will be
hmm.
7. So, we need to divide the means 5 divided by 7. That will be the resolution. So, but you are
And,
dividing like 5 by 8. So, that's why I
yes,
asked.
yes. No, it can be. Okay. So you will check it. You are right. It is resolution, but this will be this one, or you can see from here also that this we can check that what should be the number of bits. So this alpha should be with this. Now this value in this case, or you are telling this sine q bit. So in that case, this is these values qi minus 1. Okay, like that. So you check that one. What our my intention was to tell you that we are actually quantizing the sample values while we are trying to derive the digital signal out of an analog signal. Okay. And then our definitions of digital signal will be a signal which is quantized in both time and samples. Now by that word samples means the sample values. Okay. So you should not say that a signal which can have 0 and 1 is a digital signal. No. You have to say a signal which is quantized in both time and samples or sample values, that will be calling as the digital signal. Okay. Now definitely you can observe from here. So the precision, what we are telling, you can see from here that this is 1 by 2 to the power qf. I will come to that later on, this what is qf and so. And so we have this signal domain. Now if the blue lines are my signals, then you can see, let us delete some part. Then you can see that when we convert this analog signal into digital domain, we encounter some error. You can observe from here that we have actual value is this one, but we quantize to this value. Okay, and actual value is this one, but we quantize to these values. So this means that evidently or inherently, the digitization process introduces an error in the sample values, and which we will be calling as quantization error. So these are quantization error. Now why this happens? This happens because of this finite representations of the samples by the bus width, or by the bus, digital bus. Okay, that is inherent, but that will not give us a major drawback while we are computing. We can develop the different these computations with higher precisions. Now, while we are talking about precisions, so we also used in our computations earlier, you can see that fractional bits. We have used it. Now, how to represent that fractional bits, how to represent this in terms of floating numbers or fixed point numbers, that is one issue we need to think of. So that part we'll be doing in a way that let me give some example, and then we'll show you that how we can present our values with fractional numbers. Okay. Say I want to represent a 0 to 5 volt range with the bus width as 8 bits. Now 8 bits means I have 8 lines. In the bus. Okay. Now what I want to represent this with a fixed point format. Now fixed point format means if I am having a bus with say 8 and say I want that the decimal point must be at certain location where this will be my 3 bits and this will be my 5 bits, and these bits will be calling this part. So before the decimal, it is integer part. After the decimal, we call it as a fraction part. Now, in physical sense, what are these? In physical sense, these are nothing but memory locations. Okay. Okay. And therefore, this dot is virtual. It is only in our mind. But with that, we can compute. Now, how to decide this integer part? You can see this can be decided from the range of that signal, because this 5 volt needed to be represented by this, and for that, what are the number of bits we need? So 5 means in binary 0, 1, 0, right? Sorry, this is in decimal and this is in binary. So 0, 1, 0, so at least 3 bits need range. And therefore this is important. So first we decide about the integer bit, and which is 3. Then we have to place the dot, and then since our bus width is fixed to 8, so the remaining bits will be for fraction. So 3.5, and we denote that this is the format of fixed points. Okay. Now then, how to represent this 5 volt in 3.5 format? So let us check it. What is required? We need to multiply this with the number of fractional bits. And what is that in this case? It is 2 to the power 5, right? So which is nothing but 32 into 5. If you calculate, this is 160. This is in decimal. If I convert this 160 into binary, we'll get A0 in hex. And then if you expand this A0 in binary, you will see 1010 then 0, 0, 0, 0. This is in binary, right? Now you observe that we had set integer 3 bits integer component, so 1, 0, 1. So as if we place the virtual dot here, this is nothing but 5 volt represented in this Q.3 format. Any questions up to this?
No, sir.
You understood? Now let me ask that if I want to represent the same 5 volt with Q 4.4 format, how to convert this? I want an answer. Huh? Tell. This 5 volt should be multiplied by what? Hello? Hello? Give the answer.
Sir, 0101 0000.
You first say what will be this one.
Sir, 2 to the power 4.
4.
2 to the power 4. And what is that? 5 into 16. Right?
80.
80 in decimal. What is the hex corresponding to that? I think 50 hex. Is it correct?
Yes, sir, 50.
So I can represent that 0101, then 0000. Now you can see my decimal point is virtually placed after 4, and we get this integer value as 5 and remaining bits are 0. So, and now you can observe also this 2 is nothing but the binary representation. So this same concept is true or can be extended to any radix, whether it is 10 or 16 or 2. We can do it. Now, have you experienced these fixed point computations? Did you experience? Definitely, we have done this in case of, say, in our childhood days for arithmetic operations. But also, you have experienced in calculator. There is a mode called fix. So whenever you are setting that one, you will always get the results with the fixed set of precisions. Right. So that means there are certain way of computation. So now inside the computer or the processor, we'll be taking these values. We'll be taking these values. Not 5.0 or something like that. So you can now understand that even if we are going for, say, floating point or fixed point, we are basically assigning certain memory locations which are integer in actual form. So the computations are getting executed with integer format only. But we can virtually represent that number in the floating or fixed point number, and get the correct results. Okay. So what we understood from these discussions, that computations which we intended for computing this filter or transforms can be done in integer form. So all numbers, the signal values or the impulse response, the filter coefficients, all are represented in integer, and we can get the answer. We can go with fixed point number, fixed point format. Also, we can go with floating point format. Now, all these three has its own pros and cons. So accuracy wise, this is not accurate. This is moderately accurate. Okay. And this is having higher accuracy. But at the same time, which one is to be used is dependent on the accuracy we need. If our accuracy can be available with say integer value, then we can only go for integer computation. If it is doable with the fixed point values, we'll go with that accuracy level only and this floating point. But you should also be aware of that the memory requirement to store those values. So this is lowest. Again, this is moderate. And this is highest. Okay. So that means if in our system, in digital processor or embedded system, we do not have much memory, then we may have to compromise with the accuracy or optimize rather. That means instead of going into floating point computations, we can go with the fixed point format if our memory availability is moderately better than what is needed for the integer one. Okay. And then speed wise, because for floating point representation, we need more memory locations to interact with. So speed wise also floating point computations will be slowest. So in case of speed of operation. So this is fastest, the integer. Again, this is moderately speeded. And this is slowest. Okay. So what we understood from this, that representation of digital signal with the finite length of bus or finite width of bus has impact on the performance of the embedded system. And what are those performance? One is the accuracy of the computation. Second is the speed of the operation. And third one is also to be concerned about that memory requirement. So now if I increase memory to accommodate floating point computation, my system cost will be more. Okay. And if my system cost is more, that means overall product price will be more. And then there is a chance that customer will buy it less. Okay. Then apart from that, for the more memory interaction, the power consumptions will also be more, and therefore the running cost of the system will be more. If it is you are intent to use it for a portable system with battery powered, then the life of the battery is again a major concern for that system to run. Okay, is it understood?
Yes, sir.
Yes, sir.
Okay. Okay, so now we understood that how all these issues are highly related to our embedded system implementations. And then we'll come with a universal framework of our embedded system design. So we understood that all the different applications we can do with the processor, but processor need to get the signal from the external world, which are analog in nature, and therefore it should pass through an ADC, which will convert that analog signal into digital. Then all the computations will be done, and will be always be analyzing for different computation platform, different mode of computations, different way of representing this data, and accordingly we can choose a processor and the memory systems, and then we can execute all these computations. The output will be generated in digital domain, and if my system is requiring analog signal as an output, then we need to go for DAC. If it does not require, then we can directly interact with this digital signal with different peripheral devices. And then with this universal processor, we can extend with different sensing systems and the actuating systems or display unit or so. So we can have, say, any image signal or the one dimensional signal, say ECG signal, or any power signal, which I have told that, say, current signal or voltage signals. And we can also have the digital input directly from the keyboards, which are user interfaces. Then we can execute our computations within this processor. And now this processor can be any processor. Although we will be learning here this 8085 or 8051, but it can be any other processors. The remaining peripheral connections will always remain same, right? So based on your particular or specific architecture, means circuits, then we can have these LCD displays or graphical LCD displays, which can take digital output directly. Some of the relays, so like relays can take analog signal, so we need to convert it into through the AC. Some stepper motors, so these are actuators. Okay, so we can have some actuators there. And with this framework in mind, we'll be trying to learn our architecture inside the processor. So now this is what you can expect on the printed circuit board, right? And then we have two architectures. One is which is linking this processor to different peripherals, and another is what is inside this processor. So in actual means through this course we'll learn first what is inside this processor, and then how to use those architecture to interact with these different peripherals, right? Any questions?
ওই ফুল লোড প্লাস একটা হয়েছে আবার
Hello,
ইয়া করতে হবে প্যাকেটটা বলে কোনো লাভ হয়নি প্যাকেট আমাকে নিতেই দেয়নি যে আমাকে দুটোই মানে জিজ্ঞাসা করে করাতে হবে
don't take any irrelevant thing here. Ask only the question related to this, and don't talk in over phone during this time. Any questions up to this?
No, sir. Sir, can you provide the slides up till now?
No, I will not. I will not, because what I am finding that you are not, no one is actually sincere. Everyone is online, but you are doing something else. So you need to go through this video once again and then solve your doubts. I am every time telling you that you should be interactive, but you are not listening. Your response is indicating that you are not listening these videos. You just kept it on because of your attendance or so, and then you are doing something different work. So until I find this, you people are becoming interactive with me, I'm not going to give you the slides. Even sometime I will do one thing, that I will not record. So that you have to be attentive during the class only. So no recording will be there. Will that be fine?
Yes.
And in that case, what will happen, that most of you will get P. I am repeatedly telling that you must be interactive, you must be fully concentrating on the subjects during this, and try to improve your skill. And no doubts will be cleared later on. If you are insincere enough. So after this introduction, we can formally define the embedded system. Though this definition is very tentative in nature, and today's time, this boundary between the bigger systems or embedded system is becoming less and less uh, distinct. It is getting blurred rather. So, however, we can do this. A device with a programmable computer, which is the digital processor, dedicated to serve single task or a group of tasks, and cannot be used as a general purpose computer. In this case, actually, means main purpose was to make the system compact as well as make the system cost effective and accurate, so that the user can buy it easily. Okay. So for example, we have fax machine, digital clock, digital thermometer. Okay. And as I said, that PC is not itself an embedded system or embedded computing system, but with today's world, we are putting more and more features into embedded system, and it is becoming a bigger system, bigger embedded system. So regarding this memory or the number of features or number of tasks handled by the system is as equivalent to as would be with the PCs. Okay. So that boundary is not very distinct. Now these programmable computers can be the microprocessors or microcontrollers or digital signal processor. There are different manufacturers of them. or field programmable gate arrays. So all these can replace the digital processor in our framework, embedded system framework, and all have some pros and cons and different features. So in this table we have highlighted that microprocessor, microcontroller, and digital signal processor are all programmable. That means we can write code or software, or we can call it as a firmware in assembly, okay, for all these type of processor. But in case of FPGA, this is programmable as well as reconfigurable. That means inside this particular chip, our circuit is not defined. We can define it through a code, which is different than software code. Okay. Then we have these processors like general purpose CPU. In microcontroller, it is clubbed with the IO devices. Different IO controller actually is developed or integrated along with the CPU. So this is the difference between the microprocessor and microcontroller. In case of microprocessor, we'll see that peripheral controller chips are external to the processor, while in case of microcontroller, it is inside the processor chip itself. Okay. Then we have this digital signal processor, which is also having CPU, but it is having some dedicated unit, hardware unit also, which can be configured with instructions with software, which we can call it as a initialized program, or we can call it also a driver. And in case of FPGA, we have a number of components like lookup tables, multiplexer, D flip-flops, and so on. The processor can be coded with the assembly or higher level languages like C, and microcontroller also same. The digital signal processor same. Here for defining the circuit, we need this HDL, hardware descriptive language, and examples are VHDL, Verilog, or so. And then once we can also define or develop a processor itself within this FPGA, and then we can go or develop some assembly language for that particular processor, and we can go for software coding for that particular processor. That the processor will be calling as soft processor because it is written in a with a VHDL code, and it will act like a processor just like this 8085 or 8051 or so. Okay. Now instead of going with this embedded C or C language, we'll be insisting here or learning here the assembly language programming. This is because the assembly language programming is very compact compared to the high level language. The compiler is not needed, and so we'll get exact size of the memory locations required from the code itself. But wherever there is involvement of third party compiler, so there is a chance of generations of spurious codes because of the bug in the compiler itself, and therefore the memory size requirement cannot be measured with definite sense. And we may come up with the different execution time and may not be able to meet the exact one. And another part from the student means learning perspective is that we can develop a mental map of the architecture of the processor, and that will help us while we'll be going to code this. So today we'll stop here. And so with today's learning, what we learned, we started with the realizations of filter in this embedded system in digital mode. We discussed different issues related to that signal processing on the digital systems or embedded systems, and we developed the general framework for our embedded system, and then we come up with that what kind of digital processors are available in the market, and then out of that we'll be learning one such microprocessor and one such microcontroller, and which will constitute our whole course. Okay, so I will provide these slides only when I find that this class is becoming interactive.